All right, this is April 1st, 2021, AP Physics C, and I want to lecture about Chapter 12 today. There's a student out, and so I thought it'd be nice if I made a video recording of my lecture. I don't know why my alarm just went off, but too bad. Chapter 12 has the title Rotation of a Rigid Body. So as far as kinematics go, when we had a linear or translational type of situation, we had the variable x that represented position, and of course delta x would represent displacement, your change in position, defined as your final position minus your initial position, whatever reference point you pick. So it's a vector, and actually position is a vector quantity too, relative to your reference point. So if I say here's my reference point and here's my position, then I say, oh, this is 1.2 centimeters to the right of my reference point. Okay, well, that's a vector to the right of. And we also had velocity, and of course, change in velocity is your final velocity minus your initial velocity. And we have acceleration, and we have time. Those are the four variables that we've been dealing with. Of course, we had initial velocity and final velocity. I didn't bother with the two subscripts. But position, velocity, acceleration, time. We also have been dealing with mass and force and energy and work, not to be confused with weight. So great. So far, you've had all these different variables in our course. And now in chapter 12, which is on the topic of rotation, we're basically going to just about double all of the variables and expressions that you've been dealing with. So in the angular world, position has as its angular equivalent theta, the angle, again, relative to some reference point. So if I say the positive x-axis is 0 degrees, then the angle measured counterclockwise is the positive angle theta, and if it's clockwise, that's a negative angle theta. Displacement becomes change in angle. And as is true for all changes, it's defined as your final state minus your initial state. Velocity has its angular equivalent. So velocity was change in position divided by change in time. And you could also express that as the derivative of position versus time, right? Dx dt, which in shorthand, I would just write x with a single dot above it, representing change in position with respect to time. The angular equivalent is called omega. And sure enough, that would be the change in angle divided by the change in time. And it's also the time rate of change of angle. So I could write d theta dt as omega. Change in velocity, well, change in angular velocity. So of course, your final state minus your initial state, your final angular speed minus your initial angular speed. Then we also have acceleration, and that was originally defined as your change in velocity divided by change in time, or the derivative of velocity, or the second derivative of position. Same thing is true here. It's called alpha. And it would be the change in angular velocity divided by the change in time, or the second derivative of angular position with respect to time. For time, the angular equivalent is time. So that's nice. For mass, the angular equivalent is called the moment of inertia. And it has to be calculated using a formula that is mr squared summed over or integrated over, depending on how you do it, all the pieces and parts that make up the, the item that you are examining. Okay, so kind of scary, right? This is something you need to learn how to do. And you can have the same mass, but depending on how it's placed relative to a rotation axis, the moment of inertia can be quite different. For force, force was the product of mass times acceleration. Well, the angular equivalent would be called torque, and torque is the cross product of distance from the axis of rotation to the point of application of the force, of course, and that's another, advanced aspect of physics beyond the simple, oh, it's just multiply this times that. No, now it's you have to take the cross product and you have to have an origin established, and oh my goodness, more work. The angular equivalent of energy is still energy. Now, as a subset, we have kinetic energy was 1/2 mv squared. We do have something called rotational kinetic energy, and that is 1/2 I omega squared. Yeah. And then what was work? Work was the dot product of force and displacement in one dimension, or F dot delta R in 2 or 3 dimensions. Work in the angular world. And by the way, work, one way of doing it was the change in kinetic energy. So that could also be work in the rotational world, change in rotational kinetic energy would be a way to calculate the work done. You've also had momentum, the product of mass times velocity, and this is called, by the way, linear momentum. Well, there does exist a quantity called angular momentum, symbol capital L, and it's the cross product of R cross P. R cross P is the angular momentum vector. We there's a couple more interesting relationships. For example, torque is equal to the time rate of change of angular momentum. So if I want to try to express that, I could say, I suppose I could say R cross F is equal to the derivative with respect to time of R cross P. Now think about that. F is dp dt. F equals ma. So it does all fit in there. That's what I say. So off the top of my head, what I'm claiming is that now that we've arrived in chapter 12, you suddenly have twice as many physics equations and expressions that you get to deal with. There's a couple of details that I would want to toss into here, but we'll get around to that as we study chapter 12 in a little more detail. All right, so I'm looking at the first page of chapter 12 in our exciting textbook, and it says a review is highly recommended. By the way, I wrote this already, but now let's talk about a circle in a little bit more detail. Here I have a circle of radius r, of course, and this is angle theta, and I'm here and I go to there, and this arc length is s. You might remember from math class, perhaps, S is the product of r and theta. And of course, when theta reaches a value of 2 pi, then S is the entire circumference. So S is the fraction of the circumference, which is the ratio of theta to 2 pi. So if theta is pi radians, then the arc length S is half the circumference. Ta-da! Makes perfectly good sense. So what about the speed at which you're moving? You're moving at speed v. Well, that is the time rate of change of your position as a function of time. Here, I can say that your speed v is the product of r omega. Or in something closer to English, it is the derivative with respect to time of your arc length s, the distance that you travel around the circle. So if s is equal to r times theta, and if r is a constant, then the derivative of this, the derivative of position with respect to time, that's your velocity. The derivative of a constant is 0. The derivative of angle as a position of time is angle as a position of time. Time rate of change of angle, omega. So the, chain rule, whatever you call it. So this is the derivative of that. That's what I'm trying to say. If I take the derivative of this, well, the derivative of velocity with respect to time is acceleration. The derivative of a constant is just 0. The derivative of the angular speed is the angular acceleration. So that's trying to represent the Greek letter alpha. So here is yet another way of thinking of the connection between translational type quantities and rotational type quantities. In the old one-dimensional kinematic world, we had the 4 kinematic equations of motion. Well, yeah, 4. 1, 2, 3, 4. I have 5 lines. So I'll say, really, even before the course began, we said displacement was the product of constant velocity times time. In the angular world, we would say change in angle is equal to your constant angular rate times time. So if you're spinning at 1 radian per second, then after 2 seconds, you have spun through an angle of 2 radians. And yes, we're working pretty much in radians in this chapter. The first kinematic equation of motion, you might remember that one was final velocity equals initial velocity plus acceleration times time. Well, the angular corresponding equation would be final angular velocity is equal to initial angular velocity plus angular acceleration times time. The second kinematic equation of motion said change in position is equal to the average velocity, so 1/2 v initial plus v final, close parentheses, divided by 2, that's 1/2 average, that's the average velocity, times time. Well, in angular world, you could say change in angle is the average angular velocity. So omega I plus omega final, close parentheses, times time. The third kinematic equation of motion said the change in position delta x is the product of the initial velocity times time plus 1/2 times acceleration times time squared. So in the angular world, change in angle is equal to the initial angular velocity times time plus 1/2 times the angular acceleration times time squared. The fourth kinematic equation said the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. And by the way, I do want to, caution you that all of these were based on the requirement that it had to be constant acceleration, or else the equations were invalid. In the angular world, this becomes final angular speed squared, or velocity squared, is equal to initial angular velocity squared plus 2 times the angular acceleration times the change in angle. And the angular equivalent is that these would all have to be under constant angular acceleration alpha. This means I could make up any simple problem that you used to be able to solve in the translational world, but make it in the angular world. So I don't know, suppose I have an example that said, oh, I have an initial angular velocity of 3.2 radians per second. And I undergo an angular acceleration of 2.3 radians per second squared. And I do this for a time interval of 4.2 seconds. And I ask you, so what is my total change in angular position? And you say, oh my goodness, I'm glad this is just like an old kinematic equation in one dimension, because I could pretend that this means here's my initial velocity, and here's my acceleration, and here's my time, and I'm asking for change in position, and I ask which kinematic equation of motion relates position, initial velocity, acceleration, and time, and you say, oh yeah, I recognize that one. That's the third kinematic equation of motion, which says delta x is equal to initial velocity times time plus 1/2 times acceleration times time squared. So now you know what to do with these numbers. You say, oh, change in angular position is equal to omega I times t plus 1/2 alpha t squared. And you could power things up and work out the answer. It'll be the same values here, but different units. So instead of units of meters, you'll end up with units of radians in this case. And just to do it, 3.2 times 4.2 plus 0.5 times 2.3 times 4.2 squared. Assuming I typed it in correctly, I have a change in angle of 33.7 radians. So you're going to go around the circle multiple times. Each time is 6.28 radians, 2 radians. So after 5 revolutions, roughly, you're done with this example. But wait, there's more. The part that I think I want to emphasize, because I want to teach you as much of chapter 12 as I can today, right? So good, you understand all that stuff. Let's work out the issue of calculating the moments of inertia. And in order to find the moment of inertia, you first should learn how to find the center of mass for a system of particles. What do we got? We need to have a coordinate system. And you could be asked to do this in 2 dimensions at some point in your lives. So maybe I should teach you how to do it in 2 dimensions at this point in your lives. So I just, grab the sheet of graph paper, and I'm going to be kind of arbitrary and say, there's my origin. And let's say that I have, I'll do this in 1 dimension first. So I have a mass, 1, 2, 3, 4 squares. What do we call a square? Let's say the scale here is that 1 square is 1 meter. Okay, so this is 1 meter by 1 meter. Okay, so on this scale, here's my origin. Here's a point that is 4 meters off to the right, 1, 2, 3, 4, and it has a mass of 6.0 kilograms. And then over here someplace, boop, is another mass, and this one is 15 kilograms. And it's at 1, 2, 3, 4, 5, 6, -6 meters. This one was at positive 4 meters. And try not to get confused. This little m means meters, this m means mass. Good thing you pay attention every day in class. And so, where is the center of mass of this system? The formula in one dimension is the center of mass of a system is the sum of the products of mixi over the sum of mi. I is the index over every particle in your system. So in this example, this means the sum of the mass times its position for each one of these two objects. So 6 kilograms times 4 meters would be the first product. Now add to that 15 kilograms times negative 6 meters. And yeah, this is going to be a negative term here because it's to the left of our origin. So now we divide it by the sum of all the masses. What we have on the right is a 6 kilogram mass. What we have on the left is a 15 kilogram mass. And before you plug it into your calculator, in your head, you should be thinking, look, this guy is 2.5 times more massive than that guy. If this were a seesaw, and this were some big person, and this were some smaller person, where would you put the pivot point so that the seesaw is balanced? And you should be thinking in your head, well, the midpoint isn't going to work. It needs to be some point closer to the more massive object. And this is the formula for calculating where that's going to be. So you would expect before you turn on your calculator that you're going to end up with a negative value. Otherwise, become suspicious. All right, so we turn on a calculator and we type in the stuff and it says, well, 6 times 4 is 24. Minus 15 times 6. No, I'm not going to do that one in my head. Close parentheses. Now divided by the sum of 6 plus 15. And the answer is negative pi. Oh my goodness, oh my. Well, at least pretty close to pi, huh? Pretty darn close. How's that for random? And sure enough, look at how that matches where I drew the sketch. 123.14 means the center of balance is right around there, matching very darn close to my visual guess before I turned on my calculator. So the location of the center of mass is negative 3.14 meters. What would happen if I changed my origin? Suppose I set my origin to be at the location of the more massive object. That will change the numbers that go in here, but it will not change the physical location of the center of mass. It'll only change where your 0 point is on your scale. So as an example, if we chose that to be the new center of mass, then our formula says, okay, I usually work left to right. So the first one is going to be 15 kilograms times 0 meters plus 6 kilograms times, now on this new scale, The total distance is 4 plus 6 is 10 meters. The sum is still going to be 6 kilograms plus 15 kilograms. You should recognize the first term goes to 0. The second term is 60. So if you go, what is 60 divided by 21? Well, yeah, the number looks different because it's measured from a different origin. It says 2.86 meters. And sure enough, if you count from here, 1, 2, 2.86, it's the same spot in the physical world. It's just different origin for expressing your answer. All right. Now, what if it happens to be in 2 dimensions instead of just 1 dimension? So let's do a new example. And here's my origin, and now it's in 2-dimensional space, same scale as before. I'll stick one here, I'll put another one over here someplace, I'll put one here, let's say this one is my origin. Let's make this, how about 5, 8, 10 kilograms. And I say, great, tell me where the center of mass is for this 2-dimensional system. Well, the good news is this formula still applies for the x-axis. And so for the x-axis, I can just treat this as if it were a one-dimensional problem. Everything collapsed down onto the x-axis. So pretend that it's here, pretend that it's there, pretend that it's there for your calculations. So that means the x location of the center of mass, oh man, I guess we should take a 3-minute break right there. Take a 3-minute break, kids. Okay, 3-minute break went by, and I see this is 1, 2, working from left to right. 1, 2, 3, 4. So 8 times negative 4 is negative 32. For this guy, it's 10 times 1, 2, 3, 4. So add 40. And this guy is 5 times 6, so add 30. And then divide that by the sum of 15 plus 8 is 23. So negative 32 plus 30 is negative 2. Negative 2 plus 10 is 8. So I have 8 divided by 23. 0.35-ish meters is the location of the x coordinate of the center of mass. So somewhere around here. Now, the good news is in the y direction, it's exactly the same formula, but just in the y direction, meaning the y coordinate of the center of mass is the sum of the products of mi, yi over the sum of all the masses, mi. So in this problem, applying it, working left to right, I see I have 8 times 1 meter in the y direction, so that's 8, plus 10 times negative 2, so that's minus 20, plus 5 times 1, 2, 3, which is 15. And I'm still dividing it by the same sum of 23. So 15 plus 8 is 23. 23 minus 20 is 3. So 3 divided by 23 is 0.13. And so roughly around here someplace is the location of the center of mass of this 3-particle system. Great. I now bless you as being experts in doing center of mass calculations for a system of particles in 1 or 2 dimensions. But What if it's not a collection of particles? What if it is an extended continuous object? Like here is a bar. Where do you find the center of mass of the bar? You should have some intuition that says if it's uniform density, uniform thickness, uniform dimensions, then the center of bar should be in the center of it. And that is correct, right? So 1, 2, 3.5, 1, 2, 3.5. That is indeed the location of the center of mass. Oh, and there's a symbol for center of mass. I think it looks something like that. So you put that there, like this, and say that's the location of the center of mass. What if it's not uniform density? What if the density varies as a function of position? Oh, excuse me. There are such materials. Or what if it's not uniform thickness? What if it's in the shape of a right triangle? And we ask you, great, where's the center of mass for this thing? Well, not as obvious as this, but here you could find the location of the center of mass by integration. Yes, children, you could slice this thing up into a whole bunch of little uh, rectangles of width dx and height, which is a function of x, and calculate the mass of each little rectangle. And of course, the sum turns into an integral. So you end up integrating over the limits of this right triangle. Fortunately for you, there's an entire table where it's been done for you for simple shapes. And I see the table for the simple shapes is not displaying it for a right triangle. All right, so I was just interrupted by the students pointing out that I did my calculations incorrectly. I need to go back and fix them. So let me finish up my comment here. Turns out, if you happen to have a right triangle, then the location of the center of mass is 1/3 of the distance along each leg from the 90-degree corner. So in this case, if it's 3 squares up, the location of the center of mass is along this first square up from the corner. If this is 1, 2, 3, 4, 5, too bad it's not 6, then it's going to be 1 and whatever 1/3 of 5 is. What is 1/3 of 5? 1 and 2/3. So 1 and 2/3 and at 1. So here is the location of the center of mass for a right triangle. Just something you might want to have in your tool of knowledge. So 1/3 of the distance, 1/3 of the distance along each leg, measured from the 90-degree angle, gives you the location of the center of mass if it's uniform thickness, uniform density material. All right, so the student pointed out I did this all wrong. Well, mostly wrong. So let's just recalculate it with the correct values. Here's my origin. For the x component of the center of mass, I apparently got the first one correctly, which was the product of 8 kilograms times the distance of 1, 2, 3, 4 meters to the left, which makes it negative 32. For this mass, it was 10 kilograms times the distance of 1, 2, 3, 4 meters, which means it was 40 kilogram meters. For this mass, it was a mass of 5 kilograms times the distance of 1, 2, 3, 4, 5, 6. 5 times 6 is 30. So I made one mistake earlier on. I wrote a 10 because I saw the 10 and I didn't multiply it by 4 to create the product. So my calculation is off, and Notice I didn't take the trouble to kind of intuitively inspect this to see does that seem right? It, this should be pulled more to the right because this is the most massive one, and this is also pulling it to the right. And overall, there you go. Should have done that part. So negative 32 plus 30 plus 40 seems like that's going to be 38. And this is still hopefully all over 23. So getting the right answer this time, 38 divided by 23 means the x component was at 1.63. I hope I did the y component correctly. If I didn't, I'm sure the students will point it out to me. So positive 1.63 meters is the x component of the center of mass, and 0.13 meters is the y component of the center of mass. And oh well, there's one of many mistakes I make as I go through life every day. There's a lot in chapter 12. The next section sort of is trying to explain how you can do these integrations. And what let me just pull the book out for a moment and say, oh, look, see, it's a piece of cake. You break up your continuous mass into little differential elements, and then you integrate over the dimensions of the object. And here's the formula. Again, the center of mass in one dimension is independent of the center of mass location in a perpendicular dimension. So what you get in the x direction is independent of what you get in the y direction, two separate integrals. And this is basically the limit as your little differential element of mass shrinks to zero. You're dividing it by the total mass of the object. So that's the sum in the denominator, turns into that. And on the top, that summation over all these little differential tiny elements becomes an integral, where dm is the differential element of mass. Now, you're not used to that. So like it says here in the text, you have to replace that with something that you can handle from math class, like a dx or dy. And that leads to three types of densities. So you might remember that if you have, I don't know, a cylinder, and I ask you what's the density of the cylinder, you would say, oh yeah, chemistry class, I love that. That would be the mass of the cylinder divided by the volume of the cylinder. And you're, perfectly right. So this is represented mathematically with the Greek letter rho, which is density, and typical units would be like kilograms per cubic meter. You can also have a situation, so this is three-dimensional. You can have a situation that is just two-dimensional, where you have a plate of some sort, and it has uniform density, uniform thickness, and they use the symbol delta to represent the density in two dimensions, and that would be the mass of the object divided by its surface area. So that unit would be kilograms per square meter. But we can even simplify it down to one dimension and say I have a pencil or some other long, thin rod where I don't care about the second or third dimension. I'm just going to treat it like a long, thin rod of some sort. Well, the symbol they use for that is lambda, and that would be the mass of the object divided by its length. And of course, the units are kilograms per meter now. So here's 3 types of density that you might be encountering starting with this chapter. Linear density, two-dimensional or surface area density, and what you had from chemistry class, three-dimensional volumetric density. So let's try maybe a problem with this guy. Oh man, I don't have really time to do this problem, is what I'm thinking. What I can say is here, there's an example in your book of doing this. 12.2, center of mass of a rod. Kind of dumb. The center of mass is where you would expect it to be because it's uniform density, uniform thickness. But mathematically, it makes perfectly good sense to try to do that as an example. So if you chose to say that this is length L and that this is your origin, and you look at some differential element of it, to convert this little guy into from a differential element of mass into a differential element of position that you can use from math class that you're used to, you would say, oh, how much distance is there here? Or how much mass is there in this thing? Let's see if I can talk you through that. So the ratio of this little bit of mass to the total mass is the same as the ratio of this little differential element of length is to the total length L. And there is our secret conversion. So dm is to m as dx is to L. dm is to the total mass as dx is to the total length. And so dx is the mass divided by the length times this. Am I doing this the right way? No. What am I doing? M dx equals LDM. Let's just write the cross product. M dx equals LDM. And so the differential element of mass, dm, can be replaced by writing m over L dx. Now, the integral that says the location of the center of mass, oh, what am I trying to say? I'm trying to apply this formula. It was back on the previous page. The x location of the center of mass, for example, is equal to 1 over the total mass divided by the integral of x dm. That one. Okay, so I'm writing moment of inertia here when I should be writing the x location of the center of mass is equal to 1 over the mass of the object times the integral of x dm. Great. Well, you get to substitute this in for dm there. And so the integral becomes, let's see, 1 over m, the integral from 0 to L of m over L dx. Now, x dx. This x is that one, and that one is that one. Well, the masses cancel, which is nice because it's uniform mass, uniform density, and you would like that to happen. And so this becomes the integral of 0 to L. The 1 over L comes out because it's a constant, and you're doing the integral of x dx, which hopefully you recognize is x squared over 2. And you're now going to evaluate that over the limits of 0 to x, 0 to L, which means this is 1 over L times L squared over 2 minus 0. Well, 1 over L times L squared over 2 is L over 2. Ta-da. Ta-da! You have found through integration that which you should have already said off the top of your head, which was, oh, if it's uniform thickness, uniform density, then the center of mass is at the halfway point. And that's exactly what we got by integration. Makes you wonder why we do this. Because the situation isn't always going to be this simple. Let me try to push on because time is running short. They go on here and have you calculate the tip speed and such. Oh, great. And they try to have you find the center of mass of a two-dimensional object. Clearly, that's a piece of cake. They do rotational kinetic energy, and I should try to derive this at ludicrous speed. Maybe I can just point and say, look, for each little piece of a system, each little particle in the system, it has velocity equal to r omega. So everything in the system is rotating at a constant angular speed. Its tangential speed is the product of its distance from the axis of rotation to the location that we're looking at. So for this particle, that's r omega is its speed. Kinetic energy formula is 1/2 mv squared. V is r omega. So 1/2 times m times r omega quantity squared is 1/2 times m times r squared times omega squared. Well, great. So if you rearrange the term m times r squared, put that in parentheses, that is the moment of inertia. Okay, so the definition of moment of inertia is the sum over the system of particles of the mass of each particle times its distance from the axis of rotation squared. Hence, the rotational kinetic energy formula that I spewed earlier, 1/2 I omega squared. Then they do an example. No doubt I should do an example. It's left to the interested reader to do that example themselves. Here is the book of knowledge, at least as table 12.2. When you bother calculating the moment of inertia, which is an integration problem, for some simple geometric shapes, you can get a simple answer. And here's a table of those simple answers for these simple shapes. If you have a long, thin rod, like a pencil, the center of mass is in the center of the pencil. The moment of inertia, the integral, which I suppose maybe I should do this one, except we're so short on time. You end up calculating that the moment of inertia is 1/12 times the mass of this long, thin rod times the length of it squared. That's through an axis of rotation through the center of it. If you move the axis of rotation to the end of the rod, so if this is my rod, instead of rotating it through its midpoint, you rotate it about its end point, the mass doesn't change, but the distribution from the axis does. And since the moment goes as the square of that, you get a totally different moment of inertia just by shifting the location of your axis of rotation. This now says 1/3 ml squared. And in a normal classroom setting, we would do the integration that leads to this result. Then we would do the integration that leads to this result so that you would see how you get it by practicing the formula, which they do not conveniently list here. So I is not explicitly listed, but it's the integral of m, what is it? dm r squared, m r squared dm, maybe. So the table you're going to refer to, it'll be on AP test questions, they tend to give you these values for the particular problem that you're working on and say, oh, don't forget, for long thin rod about its end, here's the formula. Sometimes they might ask you to do the integration for a certain shape. So a couple things to notice. You can sum together different shapes to get the expected result. So if you have a cylinder, here's the formula, 1/2 mr squared. Here's a hoop, mr squared. All the mass is equidistant from the center. So that's the formula for moment of inertia, mr squared. Doesn't matter if it's spread out in a ring. What matters is that ring is all the same distance from the axis of rotation. So, of course, the result should be mr squared. Solid sphere, hollow sphere. Nice. Now, what can I teach you in a minute or two that matters? Oh, and by the way, here's the formula. Moment of inertia is the integral of r squared dm. Okay, great. The last thing I'm going to cover, because we're almost out of time, is the parallel axis theorem, because it's really useful and I want to teach as much as I can today. So it says this: the moment of inertia about any new axis of rotation is equal to the moment of inertia through the center of mass. By the way, the moment of inertia through the center of mass is always the lowest possible moment of inertia that you can have for any given object. Like for this pen, the lowest moment of inertia is through the center of mass of the pen. But add to that the mass of that object, like this pen, times the square of the distance, where d is distance from center of mass to new axis of rotation. Okay, down to just a couple of minutes, but let me at least give you faith that that might be a true statement. You don't need to see this information. Okay, so suppose I have a long thin rod of length L, and I have the axis of rotation to the center of mass, and it says the moment of inertia to the center of mass is 1/12 ml squared, something I'm not proving to you today. And I say, oh, I have a new axis, and it's over here at the end of the rod. What is the new moment of inertia? Well, this new moment of inertia is equal to 1/12 ml squared, the moment of inertia to the center of mass, plus the mass of this rod times the square of the distance d from the center of mass to the new axis. In this situation, this distance is 1/2 L. Okay, you guys do the math. So I have 1/12 plus 1/4 times ml squared. No doubt you realize you need a common denominator, and this is 3/12, and this is 1/12. 3/12 plus 1/12 is 4/12. 4/12 simplifies down to 1/3. ml squared is the moment of inertia to the endpoint, and that matches what the book said. 1/3 ml squared is the moment of inertia to the endpoint. You can do that by doing the integration yourself with the origin here, or you can do it by using the parallel axis theorem, which leads to the same result. Convenient. Okay, I think there's hardly anything else. They do cover it that I can thrust upon you today. Although it would be great if I could at least mention something about torque. Here's a nice little diagram. Let's just close with the diagram. I have a door. There's the hinge. If I push on the door this way, that's not going to do anything at all to open the door. If I push on it here, this is top view down. Well, yes, I can make the door open. But if I push on it here, it's way easier to open the door. And here, well, not as easy, but maybe about as hard as it is here. So this is useless, hard, kind of hard, easiest way to push the door open. What you're seeing is a visual example of calculating torque. So torque is the cross product. That means always measured from the axis of rotation to the point of application of the force, of course. So R times the magnitude of the force times the sine of the angle from R to F. In this case, that is a positive 90-degree angle. In this case, it's a positive 90-degree angle for F1, F4, they're both 90-degree angles. For F2, it's actually 180 degrees. Well, the sine of 180 degrees is 0. So this does nothing to open a door. Here, R is 3, 4 times greater than it is for that R. So the torque here is proportionally 3 or 4 times greater than the torque there if the two forces are equal. And here, you have to do the sine of the angle from this angle to that angle, or more correctly, always from R to F. So if you take R to be the positive x-axis, this is an angle of like 30 degrees. The sine of 30 degrees times this distance times that force is how much torque. And that ends our